Okay, moving on to the chain rule. This is one of the more formal type rules that you'll see in these videos. So this type of rule helps you answer questions like such. Let's say you had this particular example. It looks similar to the previous video for the power of a function rule. And so how would you address something like this, where it's kind of like the stuff inside the bracket, if that was just an x, it'd be x to the 6, which would be really easy. So the chain rule, what it does is it breaks complicated situations like this into simple things that you can deal with based on your primitive derivatives. Let's take a look at the chain rule in a more formal notation. So let's say that you had some y that is a function of u, but then u is some function of x. Then the question is, how would you find the derivative of y with respect to x? So again, y is a function of x, but it's indirectly written in terms of this intermediate function u. So what you can do is take the derivative of y with respect to u and the derivative of u with respect to x. Now, these things here are not fractions. These are derivatives. So these du's do cancel in a sense to make dy dx. You could think of them like fraction algebraically, but they are not fractions. They are rates of change. Okay, let's take a look at that first example on the cover slide here. We have 4x plus 3 all to the 6. What you can do is you can write y as u to the 6 with u equals 4x plus 3. Then the derivative of y with respect to u. So what's the derivative of u to the 6? If u was the independent variable, that'd be 6u to the 5. And the derivative of u with respect to x would be a 4. Then the chain rule says that you have dy dx, which is dy du, and du dx, which you can just plug those in as 6u to the 5 by 4, which is 24u to the 5. But what is u? U is 4x plus 3. And there you have it. Now, in the subsequent examples, these do get a little bit more dangerous, but perhaps I can take advantage of this template and do the next ones in such a manner that it's easy to follow. In this case, we have a root function or radical function. We can write this as y equals the square root of u. Now remember, root of u is u to the half. And then you would have u equals 6x squared minus 4x plus 1. So we would write here dy du. Just do some copying and pasting here. So it's this times that. We could write this a little bit nicer, right? Do here, let's do 12x minus 4 over 2 by the root of u. I'm just going to move on to another line here to finish. Trying to squeeze this in onto one slide is always entertaining. I know some derivative and integral videos that I'm going to do later will be a lot more dangerous to do this, but that's fine. That's 6x minus 2. So what I did here is I took these guys here and divided them all by 2, term by term. And the square root of u, well, what is u? Well, u is this stuff over here, so I can just plug in those things there and get the final answer. So there you have it. Again, please don't mind it all on one slide like that. I'm trying to make it nice and compact. Just highlight the answer in blue. And that's about it. Let's do one more example that gets a little bit dangerous, and I might have to rearrange the real estate. Hopefully it fits nicely. So let's take a look. This one here, we have a quotient rule tucked inside of a power rule. So what I might do is just write that down as follows. So here, how about y equals u to the 5, and then u equals this stuff inside. Now that stuff inside there will require a quotient rule. So here we go, dy du, which is of course 5u to the 4. That's easy. If I can type it, it's easy, 5u to the 4. And then du dx, which is a quotient rule. So you can dig back a couple videos ago to write down the quotient rule here. Perhaps I do need to simplify stuff here. So I'm doing the derivative of the top times the bottom minus the top derivative of the bottom over the bottom squared. Yes, this does simplify decently. So we have here x plus 3 squared. Oh, I just almost had that box perfectly. There we go. Squeezed it in. Finesse. Okay, so we have your x plus 3 minus x. That's just 3. Let me just double check that one, because again, these videos are done in one take and it's hilarious. Just check them over for a second. So there you go. There's your dy du and du dx. So we will have here dy dx, which is equal to dy du by du dx, which is equal to this thing here, multiplied by, oh, maybe not a bracket. That's going to look a little bit weird. Brackets inside of brackets. So you get that. Okay, let's clean this up a bit here. So 5 times 3 is 15. So 15 u to the 4. And then you would have this stuff on the bottom, squared like that. But what is u? Oh gosh, this is looking really dangerous. I want to restructure how I write this because it's looking a little bit crusty. But anyway, perhaps I can do that without too much difficulty on the next line. So was not expecting that one. Okay, so here we have 15 u to the 4. So u is equal to that. So 15 u to the 4. All right. Divided by that. You know, when you make questions that are a little bit tougher, I'm asking for my own sake to make things a little bit nicer next time. What you can do is split the numerator up into 2 separate fractions. So let's just deal with the denominator here. Hopefully I can fit this on one slide. As you can see, this is not a calculus question anymore. This is just playing with fractions. So actually, let's just do this. It's fun to do these on the fly. An alternative to this is to expand that out right away. But it looks like I've made it through the wilderness here. So we'll have 15x to the 4, and then you'll have your x plus 3 all to the 6. Okay, so how did I do that? Well, when you have a denominator over a denominator, you just multiply those out. So add the exponents. So 4 plus 2 is 6. And there you have it. That is your derivative. Wow, that was exciting.